Good morning all of you. Today I am going to make an audio recording for visually impaired student of organic chemistry book of Dr. G.M. Segal modern book. Name of the chapter is Structure and Bonding. Introduction to Organic Chemistry. The term organic compound was originally applied to compounds such as sugar, alcohol, oil and fats which are derived from vegetable or animal sources, that is from living organism. This was done in order to differentiate such compound from inorganic substances such as common salt, sulfur and metal, which are obtained from the mineral sources. The study of organic compound gradually began to develop as a separate branch of chemistry which come to be known as organic chemistry. The chemistry of inorganic compound was therefore distinguished by calling that inorganic chemistry. Vital force theory. In the early days of the growth of organic chemistry, it was considered impossible to prepare organic compound in the laboratory. Berzelius 1815 suggested that organic compound could be prepared only under the influence of some mysterious force existing in living organism. This force was called vital force from the Latin word via is equals to life, and the theory of Berzelius came to be known as vital force theory. However, in 1828, Wohler synthesized urea, an organic compound present in the urine of animal, from ammonium cyanate, an inorganic compound obtained from ammonium sulfate and potassium cyanate. NH4 twice SO4 plus 2 KCNO give rise to ammonium cyanate plus K2SO4. Ammonium cyanate give rise to NH2CO NH2, which is called urea. This synthesis of an organic compound in the laboratory shocked the faith in the vital force theory. In 1845, Cole synthesis acetic compound from inorganic sources and the laboratory synthesis of many other organic compounds soon followed. Consecutively, the idea of vital force theory completely discarded by 1850, and it was firmly established that formation of organic compound does not depend upon any special force. Therefore, the number of synthesis organic compound began to rise at an ever growing rate. Modern definition of organic chemistry. With the rejection of vital force theory, the major difference between organic and inorganic compound disappeared and the term lost their original significance. But organic chemistry continued to be treated as a separate branch of chemistry, although it was given a new definition. Organic chemistry is now defined as the chemistry of the compound which contain carbon as an essential constituent. A few compounds of carbon such as carbon monoxide, carbon dioxide and carbonates organic by above definition are however studied in inorganic chemistry, which deals with the study of all other elements and their compounds. The simplest organic compound are hydrocarbons, which are made up of carbon and hydrogen. All other organic compounds can be considered to have been derived from hydrocarbon by the replacement of one or more hydrogen atom by other atom of or groups. Therefore, organic chemistry can also be defined as the chemistry of hydrocarbon and their derivative. Theoretical aspect of organic chemistry. There has been a strong growth of theoretical understanding in the field of organic chemistry in the last few decades. This have been very helpful in interpreting the details such as mechanism, rate of occurrence, and the effect of temperature, concentration, etc. of the large variety of chemical reaction encountered in organic chemistry. In order to appreciate the theoretical aspect of the subject, the student must have a clear understanding of certain fundamental concepts, which are introducing a few relatively simple concepts in this chapter. Nature of bonding in organic compound. The carbon atom atomic number 6, which is common feature of all organic compound, has the electronic configuration 1s2, 2s2, 2px1, 2py1, 2pz0. Thus it has got 4 electrons in the valence shell. In order to acquire a stable noble gas configuration in its compound, carbon should either lose or gain 4 electrons or alternatively share 4 electrons. But the loss or gain of 4 electrons leading to the formation of C plus 4 or C minus 4 ion would require the supply of very large amount of energy which is not available during ordinary chemical processes. This implies that carbon cannot form in ionic bonds in its compound and must form only covalent bond. In other words, covalent bond is the bond of main importance in organic chemistry. According to orbital concept, a covalent bond is formed when a half-filled valence orbital of an atom overlaps with a half-filled valence orbital having an oppositively spinning electron of another atom. Thus, a carbon atom has got only two half-filled valence orbital 2px1 and 2py1 and therefore it may be expected to form only two covalent bonds, but in actual practice, carbon is known to have a covalency of 4 in its compound. To explain the tetravalency of carbon, it has been postulated that at the time of bond formation, the two electrons in the 2s orbital of carbon are unpaired and one of them is promoted to an empty 2p orbital. This gives rise to the electronic configuration 1s2, 2s2, 1, 2px1, 2py1, 2pz1 as shown below. In its new state, called excited state, the carbon atom has 4 half-filled valence orbitals which would be available for the formation of covalent bonds. Thus, carbon atom exhibits a covalency of 4. It may be noted that formation of 4 bonds by carbon would result in greater lowering of energy and formation of more stable molecule than if carbon were to form only 2 bonds. This extra lowering of energy more than compensate the energy needed to promote an electron from 2s to 2p orbital. This means that even though the promotion of electron is by itself not favored energetically since it takes place with absorption of energy, it ultimately leads to greater lowering of energy by enabling carbon to form 4 bonds in place of only 2 as illustrated. Thus, there is net release of 836 kJ mole inverse in the formation of CH2, while there is a net release of 1272 kJ mole inverse in the formation of CH2. Bond energy. The process of bond formation is accompanied by release of energy and the bonded state represented a state of lower energy than the individual atom. It therefore follows that an equivalent amount of energy will have to supply to break the bond. The amount of energy required to break a bond and separate the bonded atom in the gaseous state is known as bond dissociation energy or simply bond energy. It is generally expressed in kilojoule mole inverse. Thus, hydrogen molecule has a bond dissociation energy of 433 kilojoule mole inverse. It may be mentioned that bond energy is also equal to the amount of energy released when 1 mole of hydrogen atom combine with 1 mole of hydrogen atom to form 1 mole of hydrogen molecule containing 1 mole of hydrogen-hydrogen bond. It is apparent that bond energy is a measure of strength of bond. Greater the bond energy, stronger is the bond. Factor on which the bond energy depends. First, size of bonded atom. Bond energy is inversely proportional to the size of bonded atom. The greater the size of bonded atom, smaller is the bond energy. This is because in the bigger atom, the overlapping of atomic orbital is less effective. Bond length. The smaller the bond angle, higher is the bond energy. Smaller bond length means greater and stronger overlap of atomic orbital which result in greater bond energy. Third, nature of rest of the molecule. The energy required to break a particular bond between two atoms has a specific value only for that bond and is generally termed as bond dissociation energy. But when a certain bond may be present in the molecule of different substance, the actual value of bond dissociation energy of that bond will vary from one compound to the other. For instance, OH bond may be present in water as well as in methyl alcohol. The bond dissociation energy of OH bond in water is different than in energy of in methyl alcohol. In a polyatomic molecule, even the energy required to break a particular kind of bonds may have a different values. For example, the 4 CH bond in CH4 are equivalent, but the energy required to break the first bond is not same as the energy required to break the second bond, and so on. This difference in the bond energy of even the same kind of bond is due to the fact that the energy of bond depend upon the nature of rest of the molecule as well as Therefore, when giving the general value of bond dissociation energy of such bond, only the average value are stated. The average value are generally referred to as bond energies rather than bond dissociation energy. The bond energies of some bond are given in table 1.1. Hydrogen bond energy is 433. Hydrogen Cl is bond energy is 427. Hydrogen Br is 364. Hi is 297. Ch is 414. C single bond C is 347. Carbon double bond is carbon is 607. Carbon triple bond carbon is 803. Carbon oxygen is 335. Carbon double bond oxygen is 695. Carbon fluoride is 448. Carbon Cl is 326. Carbon bromide is 285. Carbon iodide is 213. OH is 464 and NH is 389. The values of bond energies given in the above table for HH, HCl, HBr and HI are their actual bond dissociation energy, while the value given for other bonds are the average bond energy. Localized and delocalized chemical bond. First is localized chemical bond. When a covalent bond is formed by the overlap of two atomic orbitals, the orbitals that result are the property of the molecule, not of individual atom. That is why the resultant orbitals are known as molecular orbitals. The elements in these orbitals are shared between the atoms involved in the bond formation. For example, let us consider the formation of a hydrogen molecule from two hydrogen atoms, each having one electron with anti-parallel spin. Relative to other, when the 1s orbital of two atom orbital, the two 1s electron become paired and begin to occupy the same molecular orbital, the probability of finding these electrons is greater in the region between the two nuclei. It is due to this concentration of negatively charged electron between the two positively charged nuclei, and the two nuclei are bound together. It may be pointed out that even though both the electrons are negatively charged, they tend to concentrate in the internuclear region due to their antiparallel spin. The net result is that electron density for the electron involving in bond formation is greatest in the region between the two nuclei. Therefore, the two paired electrons are said to occupy a localized molecule orbital, and the bond formed is known as localized bond. A localized bond may therefore be defined as the bond whose electrons are greatly concentrated in the region between the two nuclei only. A sigma bond between any two atoms, a pi bond between two atoms in the molecule have only one double bond, or the pi bond in the molecule having isolated double bond are all localized bond. Delocalized chemical bonds. To understand the concept of delocalized chemical bonds, let us consider the case of a molecule containing double bond and the single bond in the alternate position. Double bond which alternate with single bonds are said to be conjugate. For instance, 1,3-butadiene is a conjugate diene, while 1,4-pentadiene is a non-conjugated diene having isolated double bond. 1,3-butadiene conjugated alternatively double and single bond, and 1,3-pentadiene non-conjugated non-alternating or isolating double and single bond. Let us now discuss the molecule 1,3-butadiene as a typical case of formation of delocalized chemical bond. Each of the four carbon atom 1,3-butadiene is in sp2 hybridized state having 3 sp2 hybridized carbon and 1 hybridized p orbital. The 3 sp2 orbital of each carbon are used in the formation of sigma bonds with adjacent carbon and hydrogen atom, and all these bonds are localized bonds. The unhybrid p orbital of carbon atom are used in the formation of pi bond. Figure 1.3a shows unhybridized p orbital of the 4 carbon atom of 1,3-butadiene before the formation of pi bond. Overlap of p orbital of carbon 1 with that of carbon 2 and the p orbital of carbon 3 with carbon 4 is shown in figure 1.3b. However, if the molecule is planar, then the p orbital of carbon 2 can also overlap with the p orbital of carbon 3, just as it can overlap the p orbital of carbon 1 as depicted in figure 1.3. This means that there is an overlapping of p orbital of carbon 1 with carbon 2 with carbon 3 and carbon 3 with carbon 4 as shown in figure 1.3d. Therefore, all the 4 p orbital can be treated as forming bimolecular orbital which cover all the 4 carbon atom, figure 1.3e. In this condition, we do not have pair of electron mainly confined to the region between two nuclei. In other words, the bond formed are no longer localized. Therefore, a molecular orbital which is separate over the nuclei of more than 2 atoms is known as delocalized molecular orbital, and the electron present in it are termed as delocalized electron. The bond thus formed are called delocalized bond. A delocalized bond may also be defined as the bond whose electrons are spread over the nuclei of more than 2 atoms. As in the case of normal or localized pi molecular orbital, delocalized molecular orbital also consists of two electron clouds, one lying above the plane of the atom and other lying below it. Effect of delocalization of bond. The delocalization of bond has the following effect on the system involved. First, effect on the bond length. The formation of delocalized bond causes the bond length to the change from the normal value of single, double and triple bond. For example, the bond length between any two adjacent carbon atom in 1,3-butadiene is 149 pm. Neither correspond to carbon-carbon single bond length is 154 pm nor carbon-carbon double bond length 134 pm. Second is effect on movement of electron. In delocalized bond, the electron have greater freedom of movement than in localized bond. Third is effect on stability. Delocalization of bonds leads to a decrease in the energy of system. In other words, delocalization of bonds make the molecule more stable. This energy of stabilization is known as delocalization energy. For example, delocalization of 1,3-butadiene is nearly 16 kJ mole inverse. Kinds of molecule which contain delocalized bond. Delocalization of bonds is exhibited by three main kind of structure. First is double or triple bond in the conjugation. Apart from 1,3-butadiene is discussed above, benzene is another important example of molecule containing multiple bond in conjugation which exhibit delocalization as discussed below. All the carbon atom of benzene ring are in the state of sp2 hybridization. The three hybridized orbital of each carbon atom are involved in the formation of 3 sigma bond, 2 with adjacent carbon atom and 1 with hydrogen. As far as the unhybridized p orbital of each carbon atom is concerned, it can overlap to a small but equal extent the unhybridized p orbital of both the adjacent carbon atoms. Thus, the two odd electron in the unhybridized orbital of each of the 6 carbon atom can form pi electron cloud involving more than 2 atoms. In other words, the pi electron are spread over or extensively delocalized, and this results in the formation of a molecular orbital embracing all the 6 carbon atom. The net result of this delocalization is that there are two continuous ring-like electron cloud, one lying above and the other lie below the plane of atom as shown below. Second is double or triple bond in the conjugation with p orbital on adjacent atom. The presence of an p orbital which may have two, one or no electron on an atom adjacent to a multiple bond also leads to the formation of a delocalized bond. For example, in vinyl chloride CH2 double bond CH the p orbital of chlorine atom having a lone pair of electron overlap with the carbon-carbon double bond to cause delocalization as shown in figure on the right hand side. Allylic anion CH2 double bond CH minus CH2 negative affords another example of structure exhibiting delocalization in which p orbital on adjacent atom to multiple bond contain 2 electrons. Structure in which the p orbital on adjacent atom contain only 1 electron are found in free radical, while the structure in which the p orbital does not contain any electron are come across in carb-cation. Third is hyperconjugation. This type of delocalization involves carbon hydrogen sigma bond adjacent to multiple bond and is discussed later in section 1.8. Van der Waals interaction intermolecular forces. Intermolecular forces are the attractive forces which operate between molecules of the same or different substance. These forces can be divided into different types depending upon the nature of the molecule. For instance, in covalent compound containing polar bond, partial negative and positive charge are produced on atom by unequal sharing of electron pair. As a result, majority of these molecules possess a dipole moment In such cases, the negative end of one molecule will naturally attract the positive end of another molecule to give rise to intermolecular force known as dipole-dipole interaction. However, non-polar molecules also have weak intermolecular forces as discussed below. Non-polar molecule substances such as oxygen, nitrogen, chlorine and methane exist in the gaseous state in the form of individual covalently bonded molecules. But even such substances as well as noble gas undergo condensation at low temperature to liquid and solid state, which is accompanied by degrees of energy. This leads to the suggestion by van der Waals, a Dutch physicist, that there must be some weak intermolecular interaction between such molecules which become relatively stronger in the liquid or solid state. Subsequently, these forces came to be termed as van der Waals forces or interactions. They may be defined as weak forces of attraction between non-polar molecules which arise from the movement of electron in atom and molecule. That these forces are quite weak is evident from the fact that non-polar molecule substance and the noble gas have very low boiling point. This can be possible only if the intermolecular forces are weak and are overcome by supplying very large amount of energy. Origin of van der Waals forces. To understand the origin of these forces, let us consider two helium atoms very close together. Ordinarily, in each atom, the charge of the electron is symmetrically distributed around its nucleus. However, since the electron move about freely, we can imagine that at a particular instant of time, millionth of a second, the electron distribution in atom first becomes somewhat unsymmetrical with a slight increase in energy density on one side. Therefore, for a very small fraction of second, this atom have one end very slightly negative relatively to the other end. This temporary separation of positive and negative charge produce an instantaneous or temporary dipole. The temporary dipole in turn influences the electron distribution of another atom present in its neighborhood because the negative end of the atom first repel the electron of atom second. As a result, there is an instantaneous induced dipole in the neighboring atom. Although this picture persists for an extremely short time and a momentary and induced dipole are constantly changing, the next result is a force of attraction between the neighboring atom. Similarly, in case of non-polar molecules such as methane and carbon tetrachloride, the average distribution of charge about the molecule is symmetrical and there is no net dipole moment. However, the instantaneous increase or decrease in the electron density in the particular region create very short-lived temporary dipole in the portions of a molecule. These dipole induce a positively orientated dipole in the neighboring molecule so as to result in the net attraction between different molecules. The force of attraction between non-polar molecules due to temporary dipole-induced dipole instant interaction constitute van der Waals interaction. They are also known as London force or dispersion force. Factor influencing van der Waals forces. As already remarked, the van der Waals forces are weak and effective over extremely small distances. The actual magnitude of these forces depend mainly upon the following factors. First is number of electrons in the molecule. The magnitude of van der Waals force depends upon the number of electrons in an atom or molecule. With the increase in the number of electrons, there are more chances for the electron distribution to become unsymmetrical. As a result, the magnitude of van der Waals force increases. Second is size of the molecule. As the molecular size increases, the surface area becomes large. Consecutively, the chance of unsymmetrical electron distribution increases and the van der Waals force becomes stronger. Since the increase in molecular size generally runs parallel to the increase in molecular weight for the same type of substance, therefore the van der Waals force also becomes relatively stronger with the increase in the molecular weight. That is why the boiling point of a series of similar compounds generally increases as the molecular weight increases. For instance, the boiling point of alkene increases gradually from methane to ethane to propane and so on. Third is molecular shape. The magnitude of van der Waals force also depends upon the shape of molecule. To illustrate this statement, let us consider the case of N-pentane and neopentane. N-pentane is straight chain molecule having a large surface area while neopentane is a compact molecule having lesser surface area. Due to greater surface area of N-pentane, there are more chance for the molecule of this compound to interact with each other. As a result, the magnitude of van der Waals forces is large. On the other hand, the chances of molecular interaction are much less in neopentane due to compact size of the molecule. Hence, the magnitude of van der Waals forces is very small. That is why neopentane has a much lesser boiling point 283 Kelvin than N-pentane 309 Kelvin. Fourth is temperature and pressure. It may also be noted that for the same substance, the van der Waals force is relatively stronger at low temperature and higher pressure. At the low temperature, the random movement of the molecule decreases with which provide greater opportunities for molecule interaction. Naturally, therefore, the van der Waals forces are relatively stronger at high pressure. The molecule get closer so that there is stronger interaction between neighboring molecule and therefore the van der Waals forces are also stronger. Type of van der Waals interaction. It may be pointed out that apart from intermolecular forces between non-polar molecule due to temporary dipole-induced dipole interaction, the term van der Waals interaction also includes the following two types of attractive forces. First is dipole-dipole attraction. As already stated, there are forces of attraction which operates between molecules which are permanently polar in nature such as HCl, NH3, SO2 and acetone. Second is dipole-induced dipole attraction. These forces operate between molecule one of which is polar and another is non-polar. Under the influence of polar molecule, a temporary dipole is induced in that non-polar molecule. This gives rise to dipole-induced dipole kind of attraction. For example, there is a weak interaction of this type between water molecule and xenon gas due to which xenon is sparingly soluble in water. Van der Waals repulsion. The magnitude of van der Waals forces of attraction increases as the distance between the non-bonded atom or the molecule decreases. The attraction becomes maximum when the distance between the non-bonded atom or molecule reaches a certain minimum value. This minimum distance at which the forces of attraction is maximum is equal to the sum of van der Waals radii of the non-bonded atom or molecule. If non-bonded atoms come so close to each other that the distance between them is lesser than the sum of their van der Waals radii, the attractive interaction turns into repulsive interaction. For example, in the Bode conformation of cyclohexane, there is a repulsive interaction between two flagpole hydrogens. This is because the distance between them is 183 picometer, which is less than the sum of their van der Waals radii 253 picometer. Please refer to the Bode conformation of cyclohexane, section 3.25. Resonance. It has already been studied in earlier classes that concept of resonance or mesomerism was put forward to explain the structure of compounds such as benzene. It has been suggested that if a molecule can be assigned two or more conventional valence bond structure, each of which can explain most but not all the observed property of compound, the actual structure lies somewhat in between the various possible conventional structure. The various possible structure are called contributing or canonical structure, and the actual structure is called resonance hybrid. The resonance hybrid is indicated by putting a double-headed arrow between the contributing structure. The concept of hybridization of two or more conventional valence bond structure to arrive at an entirely new and individual structure, which however cannot be depicted on paper in terms of conventional formula, is termed as resonance. One of the most well-known example of application of resonance is afforded by benzene. Since benzene could not be assigned any satisfactory valence bond structure which could explain all the properties, it was proposed that benzene is a resonance hybrid of structure first and second. This implies that the structure of benzene is represented neither by one and nor by second but lies somewhat in between the two. It is evident that in resonance hybrid, the bond which link the carbon atom neither correspond to the single nor double bond. On the other hand, all the bonds are equivalent and are intermediate between single and double bond. This has been confirmed by X-ray diffraction study which shows that all the carbon-carbon bond in benzene are exactly the same length, 139.7 picometer, which is in between that of carbon single bond 154 picometer and carbon-carbon double bond length 134 picometer. The resonance hybrid structure of benzene has 151 kilojoule mole inverse of energy less than either of the contributing structure. This represents the resonance energy of the molecule It is this energy which is responsible for the unusual stability and remarkable behavior of benzene. Note: the concept of resonance does not mean that any one molecule of benzene spans a part of its time in structure 1 and the rest of time in structure 2. It also does not mean that some molecule of benzene have got structure 1 and other got structure 2. What resonance means is that any one molecule of benzene always have the same single structure which is identical with that of any other molecule and is intermediate between structure 1 and 2. Other example of resonance: carbon dioxide. Carbon dioxide is considered to be the resonance hybrid of three contributing structures as shown below. The observed bond length of carbon-oxygen bond in carbon dioxide is 115 picometer is lesser than that of carbon-oxygen double bond 112 picometer, which can be justified in terms of its resonance hybrid structure. Second is carboxylic acid. The acidic character of carboxylic acid is explained by treating the carboxylic acid as the resonance hybrids of the following contributing structure. 3. 1,3-butadiene. 1,3-butadiene and other conjugated diene also exists as resonance hybrid. For example, 1,3-butadiene is a resonance hybrid of the three contributing structure. Use of curved arrow to show interconversion of contributing structure. Since contributing structure differ from each other only in the position of electron, curved arrow are often used to show the flow of electron in the conversion of one structure into other. This makes it easier to draw the various contributing structure of given species. For example, the contributing structure of carboxylic acid may be drawn as shown below. Similarly, the contributing structure of 1,3-butadiene may be drawn as follow. Condition for resonance. According to the general theory of resonance, the various conventional structure formula contributing to the structure of resonance hybrid must satisfy the following condition. First, the various contributing structures should differ from each other only in the position of electron, pi electron and lone pair of electron, whereas the relative arrangement of atom or atomic nuclei to be more precise, and their state of hybridization must be same. Note: it may be recalled that existence of structure having the same molecular formula but different relative arrangement of atomic nuclei leads to the phenomena of isomerism. Second, the atom involved must lie in the same or nearly the same plane. Third, the number of paired or unpaired electrons in each contributing structure must be same. For example, CH2, CH, double bond CH, single bond CH2 is not valid contributing structure for butadiene, CH2 double bond CH, single bond CH, double bond CH2, since it has more unpaired electron than other contributing structure. Fourth, all the contributing structure must show the correct number of valence electron. For the element of second period, no contributing structure should have more than 8 electron in the valence shell of element. For example, CH2 single bond CH double bond NH3 cannot be considered as a contributing structure since in it nitrogen has 10 electron in its valence shell, which is not possible. Fifth, all the contributing structure should have the same or nearly the same amount of energy and stability. Sixth, when the contributing structure differ in energy content or relative stabilities, the more stable structure makes greater contribution towards the resonance hybrid. Seventh, in determining the relative stabilities of contributing structure, the following point must be noted. First, larger the number of covalent bond in the structure, the greater is the stability. For example, CH2 double bond CH, single bond CH, double bond CH2 is more stable than CH2 positive, single bond CH, double bond CH minus CH2 negative is less stable. The structure involving separation of positive and negative charge are less stable than those which do not involve any separation of charge. Third is when atoms of different electronegativities are involved, the structure having negative charge on the more electronegative atom and positive charge on less electronegative atom are relatively more stable than the other way round. Fourth, the structure having like charge on adjacent atom are highly unstable. Eighth, the more the number of contributing structure, the more stable is the resonance hybrid. Properties of resonance hybrid. First, stability. A resonance hybrid is always more stable than any of the contributing structure. The extent of greater stability of the resonance hybrid depend upon the number of contributing structure and their relative stabilities. Second, resonance energy. It is a measure of stabilization due to the resonance and may be defined as the difference in the energy between the energy of the resonance hybrid and its most stable contributing structure. Greater the resonance energy, greater is the stability of resonance hybrid. For example, the resonance energy of benzene is about 151 kJ mole inverse. The value of resonance energy can be determined from the data involving heat of hydrogenation and heat of combustion, etc. Third, bond length. In a resonance hybrid, the bond lengths are different from those in the contributing structure. For instance, the carbon-oxygen bond length in carbon dioxide is 1.15 angstrom as against the value of 122 picometer for the carbon-oxygen double bond length. It may also be seen that the concept of resonance hybridization is essentially equivalent to the delocalization of electron. It is this delocalization of electron which leads to the formation of stronger bonds and more stable molecules. Therefore, the term delocalization energy is often used in the place of resonance energy. Resonance effect. It is the process of permanent displacement of electron in the molecule brought about the resonance or mesomerism, generally designated as R or M effect. Unlike inductive effect, resonance or mesomeric effect is transmitted through pi electron and operates in unsaturated system, particularly those containing a suitable atom or group in conjugation with unsaturated system. For this reason, it is termed as a conjugative effect. What happens is that resonance effect cause delocalization of electron and give rise to an additional contributing structure due to the withdrawal or release of electron by the given group. For example, in the molecule CH2 double bond CH, single bond CH double bond O, which contains C double bond O group in the conjugation with C double bond C. Electron withdrawal by C double bond O group cause delocalization of electron and give rise to an additional structure as shown below. Type of groups involved in resonance and their resonance effect. First, group having electron withdrawing resonance effect, minus or minus M effect. Groups such as NO2, C double bond O, C triple bond N, SO3H and C double bond OR withdraw electron from an unsaturated linkage through resonance and are said to have minus M or minus R effect. Second, group having electron releasing resonance effect plus R or minus plus R or plus M effect. Groups such as OH, OR, NH2, NHR, NR2, which can release electron through resonance, are said to have plus M or plus R effect. These groups have one or more lone pair of electron which they furnish for conjugation with the unsaturated system. It is important to remember that unlike inductive effect, resonance effect suffers practically no decrease in intensity with the increase in distance along the chain of atom. Application of resonance effect. Resonance effect is very useful in explaining the stability, isoformation and reactivity of main chemical species as illustrated below. First, low reactivity of vinyl halide and aryl halide. As compared to alkyl halide, vinyl halide exhibits very low reactivity in nucleophilic substitution reaction. This is because the halogen atom in vinyl halide cause delocalization of electron due to plus R effect and give rise to an additional contributing structure as shown below. Due to the resonance stabilization, the halogen atom gives more firmly attached to the carbon and is not replaced readily. Similarly, low reactivity of aryl halide towards nucleophilic substitution can be explained in the term of resonance stabilization. Second is acidity of carboxylic acid. The acidic nature of carboxylic acid is due to their ionization in aqueous solution to form carboxylate ion and hydronium. The carboxylate ion is stabilized by resonance due to minus R effect of C double bond O group. This makes the formation of this ion easily possible and is mainly responsible for the acidity of carboxylic acid. Even in undissociated carboxylic acid, resonance is possible, but this involves separation of charge. As such, it must be much less effective than in carboxylate ion, where the resonance forms are identical. Therefore, carboxylic ion is stabilized by resonance due to the greater extent than carboxylic acid, which can explain the tendency of carboxylic acid to undergo ionization. We will encounter many more examples of resonance effect in explaining the cause of ease of formation, relative stabilities, and hyperconjugation or no bond resonance. The concept of hyperconjugation was put forward by Baker and Nathan 1935 as a result of certain observation concerning the inductive effect of alkyl group attached to an unsaturated system such as double bond or benzene ring. An alkyl group has electron releasing inductive effect plus I effect, and the other of the plus I effect of different alkyl group is CH3 thrice carbon less than CH3 twice CH is less than CH3, CH2 less than CH3. But when an alkyl group is attached to an unsaturated system such as a double bond or a benzene ring, the border of inductive effect gets reversed. To account for these observations, Baker and Nathan put forward the concept of hyperconjugation, also known as Baker-Nathan effect. Hyperconjugation is another kind of resonance or delocalization of electron which take place through overlap between a p orbital and a pi electron and a sigma orbital of an adjacent carbon-hydrogen bond. For instance, let us consider the delocalization of electron in the alkene CH single bond CH double bond CH2, where CH represent an alkyl group attached to C double bond C. The delocalization here may be shown as. It is clear that the delocalization involves overlapping between a sigma orbital of CH bond of alkyl group and the pi orbital of C double bond C bond. As a result of this overlapping, each of the delocalization electron is involved in binding together not merely two atoms, but it helps in binding together all the four atoms to same extent. In terms of resonance, the above situation may also be taken to mean that the given alkene is a resonance hybrid of canonical form such as first and second. CH single bond CH double bond CH2 CH positive double bond CH single bond CH2 negative. It may be seen that hydrogen is not forming any real bond in structure second. Therefore, hyperconjugation is somewhat also called no bond resonance. It is important to remember, however, that in actual practice, hydrogen is not free to leave its original position because structure second is highly unstable and make only minor contribution to resonance hybrid, which resembles structure first very closely. Whether we look at hyperconjugation in terms of orbital overlap or resonance, what happens is that there is interaction between sigma electron of CH bond and pi electron of adjoining C double bond C bond. In actual practice, this means that CH bond of alkyl group is slightly less than a single bond. C2 C3 bond has some double bond character, while C1 C2 bond has some single bond character. These conclusions are supported by the experimental determination of various bond length in propene and other alkene. It may recall that normally resonance delocalization of electron involves pi electron of two or more conjugate double bond or pi electron of one double bond and p electron of an adjacent atom containing non-bonding electron. Explanation of observed order of inductive effect of alkyl group when attached to a benzene ring or any other unsaturated system such as CH double bond CH2. It has been stated above that the unusual electron releasing inductive effect of alkyl group follows the order CH3 3 C less than CH3 twice CH CH3 CH2 less than CH3. But when attached to a benzene ring or any unsaturated system, the order of the inductive effect becomes CH3 less than CH3 CH2 less than CH3 twice CH less than CH3 thrice C. This may be understood as follows. When a methyl group is attached to an unsaturated system as in propene, CH3 single bond, CH double bond, CH2, the various hyperconjugative structure possibles are. On the other hand, when an ethyl group is attached to an unsaturated system as in 1-butene, CH3, CH2, CH double bond CH2, the number of hyperconjugation structure possible is lesser as shown below. This is because the number of hyperconjugative structure possible depend upon the number of alpha hydrogen atom. Hydrogen attached to the carbon called alpha carbon, which is directly linked to the unsaturated system. Since only these hydrogen participate in hyperconjugation, Now ethyl group has only 2 alpha hydrogen, whereas methyl group has 3 such hydrogen. Similarly, the number of hyperconjugative structure possible for CH3 twice CH will be still lesser than no such structure will be possible for CH3C. As the number of possible hyperconjugative structure goes on decreasing, the electron releasing tendency of alkyl group goes on decreasing. In the hyperconjugation, in neutral molecules such as alkene, the hyperconjugative form displayed not only no bond resonance but also charge separation not shown by the main form. This can be easily seen from the example of propene and 1-butene shown above. This kind of hyperconjugation is called sacrificial hyperconjugation. In case of free radical and carbocation discussed in section 2.5 and 2.7, the hyperconjugative form involves only no bond resonance but no charge separation not shown by the main form. This is known as isovalent hyperconjugation. Application of hyperconjugation. The concept of hyperconjugation is widely used in the study of organic chemistry. For example, it helps to explain the relative stabilities of alkanes. It is used to explain the relative stabilities of carbocation and free radical. Inductive effect. The concept of inductive effect concerns the shift of electrical charge within a molecule arising out of the presence of polar covalent bond in the molecule. To illustrate this, let us consider a molecule having a chain of carbon atom with a chlorine atom linked to the and carbon atom, such as C4, C3, C2, C1, Cl. Due to greater electronegativity of chlorine, the electron pair of the bond between C1 and Cl is displaced towards the chlorine atom. As a result, polarization of the bond takes place. Chlorine acquires a small negative charge while C1 becomes slightly positive charge as shown below. Now the positively charged C1 exert an attractive influence upon the electron pair shared between C1 and C2 due to the resultant electron displayed towards C1. The positive charge on the C1 is partially neutralized while a small positive charge developed on C2. But the charge on C2 is smaller than that of C1. The positively charged C2 in turn attracts the electron pair of bond between itself and C3, thereby making C3 also very slightly positive charge. This process of electron shift along the chain of carbon atom due to the presence of a polar covalent bond in a molecule is known as inductive effect. It is represented by the arrow as shown below. Inductive effect is somewhat also called transmission effect because it is transmitted through the bond constituting the chain of atom. It should be noted that the effect along the chain of atom is not the same throughout. It decreases sharply as we move away from the initial polar bond and is negligible from fourth atom upward. It must also be understood that the inductive effect does not involve any actual transfer of electron from one atom to the other. It merely happens in displacing them permanently. Type of inductive effect. Inductive effect is relatively effect and may involve attraction and of electron towards a group or repulsion of electron away from it. For comparing the relative inductive effect of various groups, hydrogen is commonly taken as the standard and accordingly groups are divided into two categories. First, electron withdrawing or attractive inductive effect denoted as minus I effect. Atom or group which have greater electron attracting capacity than hydrogen are said to have minus I effect. The decreasing order of minus I effect of some common group is as follows: Nr3, Sr2, NH3, NO2, SO3H, Cn, C double bond OH, fluorine, chlorine, bromine, iodine, OC6H5, C double bond O, R, OR, OH, C6H5. Minus I effect decreasing order. It may be noted that compared to hydrogen atom, most groups are electron withdrawing. Electron releasing or repelling inductive effect, denoted as plus I effect. Atom or group which have lesser electron attracting capacity than hydrogen are said to have plus I effect. The most important electron releasing groups are alkyl group. At the same time, many groups having formal negative charge and atom of low electronegativity such as Si, Mg and Li are electron releasing. The decreasing order of some group having plus I effect is as follows: O negative, C double bond O negative, CH3 thrice C, CH3 twice CH, CH3, CH2, CH3, D. It may be noted that in case of alkyl groups, the more highly substituted the alkyl group, the greater is its effect. Application of inductive effect. Inductive effects play an important role in organic chemistry as illustrated below. First, comparison of relative acidic strength of organic acid. In aqueous solution, a carboxylic acid exists in equilibrium with the carboxylate ion and hydronium ion, that is Rc double bond OH plus H2O. Equilibrium sign Rc double bond O negative plus H3O positive. The strength of the acid is generally expressed in the term of equilibrium constant Ka, known as acidity constant, which is given by the expression K is equals to Rc double bond O negative bracket H3O positive upon may Rc double bond OH. Since K is directly proportional to the concentration of hydronium ion, it would have a low value in case of weak acid and a very high value for strong acid. The position of equilibrium in the reaction between a carboxylic acid and water to furnish carboxylate ion and the hydronium ion depend upon the stability of product relative to the stability of the reactant. Rc double bond OH plus H2 equilibrium sign Rc double bond O negative plus H3O positive. Any factor which stabilizes the carboxylate ion more than the parent acid should increase the acidity, and any factor which destabilizes the ion should decrease the acidity. A group having electron withdrawing inductive effect, say G, on the carboxylate ion attract electron towards itself and thus disperse the negative charge on the anion. As a result, it stabilizes the carboxylate ion and thus increase the acidity of the parent acid. A group having electron inductive effect, say G dash, on the carboxylate ion intensifies the negative charge of the anion and thereby destabilizes the anion. Consecutively, it decreases the acidity of the parent acid. In short, it may be stated that electron withdrawing group increase the acidity while electron releasing group decrease the acidity of carboxylic acid. Let us for instance compare the acidities of acetic acid and chloroacetic acid. It is found that chloroacetic acid is more about 80 times stronger than acetic acid. This is due to the fact that acetic acid, the strong electron releasing inductive effect of methyl group, destabilize the carboxylate ion. On the other hand, the chlorine present in the chloroacetate acid exert an electron withdrawing inductive effect and thus stabilize the carboxylate anion by dispersing its negative charge. Similarly, it can be explained why acetic acid is weaker than the formic acid. Acetic acid contains CH3 group having the electron releasing inductive effect attached to the carboxylic group, which destabilizes the carboxylate ion by intensification of charge. On the other hand, formic acid has only a hydrogen which have no destabilization effect on the carboxylate ion. Second, in comparison of relative basicities of amine. Like ammonia, all the amines are basic in nature. A convenient way of expressing the basic strength of amine is in terms of equilibrium constant Kb, known as basicity constant, which is derived from the following equilibrium. RNH2 plus H2O equilibrium sign R positive NH3 plus OH negative. Kb is equals to bracket start R positive NH3 bracket close next bracket start OH negative bracket close by may R NH2. The greater the value of Kb, the greater is the basicity of the amine. The basicity of amine depends upon the availability of electron pair on nitrogen atom and the stability of the substituted ammonia ion formed. Any factor that increase the availability of electron pair on nitrogen or increase the stability of ammonium ion relative to the parent amine will increase the basicity of amine. On the other hand, any factor that has the opposite effect will decrease the basicity. It has been found that aliphatic amine have greater basicity than ammonia. This can be explained in terms of electron releasing inductive effect of alkyl group. Aliphatic amine contain one or more alkyl group in the place of hydrogen atom of ammonia. Now an alkyl group being electron releasing increase the electron density on nitrogen and thus make the electron pair on nitrogen more available for sharing. At the same time, the electron releasing inductive effect of alkyl group decrease the positive charge of the substituted ammonia ion formed by the amine and thus increase its stability. It may be noted that due to inductive effect, along a tertiary amine should be more basic than a secondary amine, which in turn should be more basic than a primary amine. Then the actual order is not found to be same always. This is because relative basicities of primary, secondary and tertiary amine can not be explained in the term of inductive effect alone. There are also other factors which plays their role. This is discussed in detail at the later stage. Third is comparison of basic strength of ethylamine and acetamide. Ethylamine is much stronger base than acetamide. This is because the plus I effect of ethyl group with ethylamine increase the electron density on the nitrogen which get easily protonated. On the other hand, the electron pair on nitrogen of acetamide get delocalized due to resonance. As a result, electron density on nitrogen decrease and its basic character suppressed. Comparison of relative stabilities of species such as carbocation and carbanion. Fifth is cause of reactivity of many compounds. Inductive effect help in the understanding the cause of reactivity of many compounds. Next is comparison of resonance and inductive effect. Resonance effect operates in unsaturated system, particularly in conjugated system through the pi electron, whereas the inductive effect is operate even in saturated system. In the presence of unsaturation is not necessary condition. Second is resonance effect involves displacement of non-bonding and pi electron, whereas inductive effect involves displacement of sigma electron. In the resonance effect, during the resonance, electron pair is completely transferred, leading to the development of full positive and negative charge. Whereas in inductive effect, the electron pair is only slightly displaced from its position so that only partial positive and negative charge appear. In the case of resonance effect, it leads to the delocalization of electron, whereas in inductive effect, no delocalization of electron take place. In the resonance effect, it is transmitted over large distance without undergoing any change in the intensity, whereas in inductive effect, it decreases sharply with the increase in distance and operates only over short distances. Electromeric effect. Electromeric effect is a temporary phenomena which operates during some reactions involving molecule containing double or triple bonds. It consists of an instantaneous and complete transfer of a shared pair of electrons of the multiple bonds to one of the bonded atom due to the requirement of some attacking reagent. Electromeric effect is usually denoted as E effect, and the transfer of electron taking place is represented by a curve arrow as shown below. Since A loses its share in the electron pair of B, A acquire a positive charge and B get a negative charge. This structure is evidently not so stable as the normal structure and is formed only at the moment of reaction under the requirement of attacking reagent. If the attacking reagent is withdrawn without the reaction being allowed to take place, electron distribution reverts to its normal state. In other words, electromeric effect involves temporary polarization at the seat of multiple bond. An electromeric shift of electron proceeds most reaction involving addition to a multiple bond. Let us for instance consider a molecule containing a carbonyl group C double bond O. When a reagent such as Cn negative ion attack the carbonyl group, one of the shared pair of electrons, the pair constituting the pi bond, is transferred to oxygen. As a result, the carbon atom becomes positively charged while oxygen acquires negative charge, and the attacking reagent immediately form a bond with a positively charged carbon as depicted below. It is quite obvious that the electron pair cannot be transferred to the carbon atom because oxygen is more electronegative as compared with carbon. Type of electromeric effect. Electromeric effect can also be divided into two types as explained below. Plus E effect. When the pi electrons are transferred to that atom of multiple bond which get bonded to the attacking reagent, electromeric effect is known as plus E effect. Minus E effect. When the pi electrons are transferred away from the atom of the multiple bond which get bonded to the attacking reagent, electromeric effect is known as minus E effect. Significance of electromeric effect. Electromeric effect is very helpful in explaining the mechanism of addition reaction of organic compound containing the multiple bond, as will be seen at different places in the text. Both the inductive and electromagnetic effect operate together. These may assist or oppose each other. In case of they oppose to each other, the electromagnetic effect generally overcome the inductive effect. Comparison of inductive and electromagnetic effect. Inductive effect. It is a permanent effect which involves a mere displacement of electron, whereas electromagnetic effect is a temporary effect which involves the cleavage of a multiple bond and the complete transfer of shared electron pair to one of the atom. In case of inductive effect, there is only a distortion in the shape of molecular orbital containing the displaced electron. The electron do not leave the molecular orbital. The electron pair of the multiple bond leave its molecular orbital completely and in transfer to the one of the atom. In case of inductive effect, the only requirement for this effect to operate is the presence of some polar bond in the molecule. It is not necessary for the molecule to contain a multiple bond. But in case of electromagnetic effect, the molecule containing at least one multiple bond which may or may not be polar in nature. In case of inductive effect, it does not require any outside attacking reagent. In case of electromagnetic effect, it can take place only under the influence of an attacking reagent. In case of inductive effect, it involves a partial separation of charge, but in case of electromagnetic effect, it involves a complete separation of charge. Thank you.